Hello everybody, my name is Giovanni Sileno from the University of Amsterdam, and I will now present a paper that I brought together with Jean-Louis Dessalles from Telecom Paris. In our daily life, as humans, we experience a variety of patterns, tendencies, rules, laws, as much as their absence. And for doing so, we don't need to take into account quantum mechanics. But the phrase "we live in a probabilistic world" makes sense also from a paradigm point of view. Probability theory started by investigating gambling, but today it has grown to be the most important ingredient of almost all formal accounts that deal with the how rational agents, artificial or natural, reason in conditions of uncertainty. It is also the fundamental basis of Shannon's theory of information, according to which the information of a certain message is equal to minus the logarithm of the probability of the occurrence of that message. A central role for this success has to be given to Bayes' rule, as this formula is used for Bayesian models, including Bayesian networks, for Bayesian inference, for maximum a posteriori estimation in statistics, and also it is a core component of machine learning methods, as for instance the variational autoencoders. Bayes' rule has been applied successfully in applications supporting or reproducing human decision-making, for instance in medical diagnosis or for evidential reasoning in criminal court settings. But it has also been used to build cognitive models of animal learning, visual perception, motor control, language processing, forms of social cognition, and etc. Overall, we can divide these uses in two types of accounts: prescriptive accounts that are about how agents should reason, and descriptive accounts that are about how agents do produce inferences. So if we have to sum up the pros and cons of probability theory, on the one hand, we can certainly identify the clarity of the theoretical framework and the proven practical value. But then, on the other hand, we can see that as a formal system, probability theory relies on a series of axioms, for instance, a measurable space of events. But our experience of the world defies this closure, because we can always find a new dimension that wasn't introduced before. And second, as a modeling framework, several cognitive patterns have been recognized, often called biases or fallacies, that are not predicted by probability theory. In particular, there is a mismatch between what humans perceive as informative and what is informative according to Shannon's notion of information. Simplicity theory is a computational model of cognition whose investigation started just by observing this informativity mismatch. Let's consider a source of noise. According to Shannon's theory of information, this is maximally informative, but a picture of noise is not informative in human terms. Simplicity theory has been found to predict diverse human phenomena that are related in general to relevance, and has also been used for experiments in artificial creativity. From a formal point of view, simplicity theory builds upon algorithmic information theory. In algorithmic information theory, the complexity of a string is the minimal length of a program that, given a certain optional parameter, produces that string as an output. This is also called Kolmogorov Complexity. It depends on the underlying Turing machine that is used to run the program. Notice that there is a difference between Kolmogorov Complexity, which is how much information is needed for a program to construct the object, and algorithmic or time complexity, which is how much time or space is needed for running that program. So Kolmogorov complexity is generally incomputable, and this is due to the halting problem, but it is computable if we assume bounded Turing machines. We will denote bounded complexity with C. So simplicity theory starts from the observation that humans are highly susceptible to complexity drops. That is, for them, situations are relevant if they are simpler to describe than to explain. This can be formally captured by the formula of unexpectedness, which is expressed as a divergence of two complexities which are computed on two distinct machines. So we have causal complexity, which is computed by a word machine, minus the description complexity, which is computed by a description machine. Diagrammatically, we see that the first machine is about constructing the situation from the word, and the second one is about constructing the situation from the mind. A few examples. So for instance, humans find in a lottery draw 1111 more unexpected than 64178, even if the lottery is fair. And this is because the first one is descriptively simpler. Another example, meeting by chance an old friend abroad is more unexpected than meeting any other unknown person. This paper aims to provide further arguments in support to non-probabilistic computational models of cognition, and in particular we focus on the following conjecture. that Bayes' rule is a specific instantiation of a more general template which is captured in simplicity theory by unexpectedness. Bayes' rules can be found easily from the definition of conditional probability, just by a simple inversion. So in this formula, we have the probability of the model given a certain observation is given by the probability of the model and the observation divided by the probability of the observation. Bayes' rule is also often informally rewritten as posterior is equal to likelihood multiplied by prior divided by evidence. In previous works, it has been hypothesized that unexpectedness offers a non-extensional measure of posterior subjective probability. If we start from this hypothesis, then we can look for a mapping from unexpectedness to the rule of Bayes. And indeed, we can see that there is a correspondence. Just by making an inversion and computing the logarithm, we can find items which just correspond to the formula of unexpectedness. But then we have an important problem, because unexpectedness has just one parameter, while the posterior has two parameters. Let's investigate then these two terms. So the first term is causal complexity. The causal complexity is the length in bits of the shortest path that, according to the agent words model, produces the situation. So the causal path is temporally unfolded. The complexity of the sequential composition is given by the strength of the causal link plus the causal complexity of the cause to appear. Because it is a Kolmogorov complexity, then the cause can be omitted if it lies in the shortest path, so if it is the best cause. So that means that in practice, the unexpectedness formula abstracts the causally explanatory factor. Let's look at description complexity. Description complexity is the length in bits of the shortest program that determines the situation. Determination, for instance, could correspond to retrieve that situation from memory. So informationally, we need to specify the address where to look at. So that means we need to specify an encoding. Actually, a theoretical link can be established through optimal encoding in Shannon's term. And indeed, in the proposed mapping, the description complexity corresponds to the probability of observation. However, complexity is much more general measure because we can consider in it also compositional effects, for instance, like a Gestalt, that can be captured by adequate mental operations, for instance, repetition, symmetry, alternance. Now we confirm our conjecture that Bayes' rule can be seen as specific instantiation of unexpectedness that makes a candidate cause explicit and does not select the best one, and takes also a frequentist-like approach for encoding observables. Why this is relevant? Well, first of all, unexpectedness is a more generally applicable measure because it doesn't require closure to compute it. In the paper, we show also that it can be used to build an informational principle of framing, a model of derived likelihood, and an explanation of the prosecutor fallacy. So let's start from the first one. We start from a famous way of saying in probability theory that says that all prior is posterior of some other prior. So let's us consider then an additional prior in Bayes' formula. This E stands for a sort of environmental context. If we follow probability theory, then we have two equivalent formulations for the posterior, because indeed we could just extract here the PDE from both of them and they would simplify. When we rewrite these two terms in terms of complexity, they are not equivalent. Let's abstract the cause C as before, and then we obtain two measures of unexpectedness. So we can compute analytically the difference between the two formulations. And in order to do so, we apply two distinct chain rules. So the first one, we already saw it, and then we have a second one for the description machine. Notice that there is a difference indeed between the two, because on the one hand, we have that the temporal constraint is dropped, and on the other hand, we acknowledge that describing E and S at the same time may be simpler than fully determining one term before the other. This can be explained in terms of informed search. When I know that I want to build the two of them, then I may have access to information that simplifies the search. Then let's apply the two chain rules and we obtain that the difference of the two formulation is superior or equal to the unexpectedness of the environmental situation E. This implies that the necessary condition for which the two formulations may be equivalent is that the contextual prior is not unexpected. That means that the contextual prior belongs to shared facts, defaults, but also to improbable but descriptively complex situations. This offers us an informational principle of framing. All contextual situations which are not unexpected provide grounds to be neglected. The remaining situations provide the relevant context for the situation in focus. The second component that we will look at is derived likelihood. Following simplicity theory, we don't have direct access to causal complexity. We need always to pass through a descriptive step to identify what to compute. So how can we estimate likelihood? Counting back the description complexity. So let's consider an example. Let us consider the estimation of the likelihood that the wall changes color if I close the door. Description complexity is almost zero because these elements are just in front of me. The causal complexity is very high because this never occurred. Then this means that this would be implausible if it occurred, and also that it is improbable to occur. On the other hand, if we consider the likelihood that a stone in the world moves if I close the door, description complexity is very high because I need to specify of which stone I'm talking about, and also in this case the causal complexity is very high. Then it is plausible that a stone will move, but it is improbable to occur. Notice also that if the stone is in the room or it was part of a story, then we return to the first case. The third point that we observe by means of the conjecture is the prosecutor's fallacy. So suppose that the probability that a certain evidence appears on a crime scene if the defendant is guilty is deemed very high. So the prosecutor's fallacy occurs when the probability that the defendant is guilty, given that there is DNA evidence, is also conducted to be comparatively high. So this is a fallacy because if we consider Bayes' rule, we see that it neglects the Bayes rates. So let us reframe the problem in terms of complexity, and we introduce the definition of causally constrained unexpectedness, which is computed just before the selection of the best cause in the normal formula of unexpectedness. So this causally constrained unexpectedness maps directly to the posterior. Then if we apply the chain rule, we see the internal component maps to the likelihood. Now, we know that this term approximates 0 because the likelihood is almost 1. So if the procurator finds plausible that the suspect is guilty, which is, I guess, a sound hypothesis, then we have also the unexpectedness of C is approximately 0. So that means that this complexity is almost equal to this one. And we can write that in this way. Then, if we consider also the limited number of suspects and the proximity to the victim, the complexity of describing the crime action is not too different from the complexity of describing the crime outcome. So that means that overall, the causally constrained unexpectedness is equal to 0. So that the prosecutor's fallacy emerges when we map components into complexity terms. Remarks for the conclusion. So the proposed conjecture provides further arguments in support to non-probabilistic computational models of cognition. We have shown that a complexity-based account allows distinguishing between relevant and irrelevant contextual elements, while the probabilistic account treats them equally. We have still open questions, obviously. For instance, how the underlying machine should be defined, which type of operator should be considered. But yet we were able to show that the abstraction level provided by algorithmic information theory was already relevant to draw insights on cognitive processes, as we've shown here, for instance, with the analysis of the prosecutor's fallacy. Thank you very much for your attention.